My dear student, colleagues, and all the viewers who are watching this program live from Facebook page Physics Center and School of Astrophysics and Astronomy and YouTube channel Pretam. I'd like to welcome you all to our international physics webinar. So, hope you are well and safe from Corona pandemic. So, as we know that we are staying in a Corona pandemic situation, so it's very difficult for us to continue our normal academic program inside the campus. So we have to start our online program. And I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including International Physics Webinar. So we are trying to adjust with this new normal situation, and we have successfully completed our 176th International Physics Webinar. Today it's our 177th International Physics Webinar. And we have with us here today Dr. Aalok Misra, Sir, Professor of Physics, Indian Institute of Technology, RoorkeeRoorkee, India, and he has already connected with us. So I'd like to welcome our speaker, Sir. Good afternoon, and
Thank
thanks
you.
for joining with us, and thanks for giving us opportunity to attend such an important webinar.
My pleasure.
So for those who are new, I'd like to inform you all that. So you can ask question by commenting in Facebook and YouTube, and you can also join with us in the discussion session. So I think you have already come to know the title of this today's International Physics webinar. Title is the Mathematics of QCD from Cone, and our speaker is Dr. Aalok Misra, Professor, Department of Physics, Indian Institute of Technology, UK, India. So now it's time to go to our speaker, sir. It's your time. You can start your session. So you can share your file or share your board.
Okay. Can you see me writing hi on the screen?
Yes, yes, yes.
Okay, great.
Let's see.
Okay, so thank you, Dr. Das, for the kind invitation, and it's my pleasure to be able to join virtually with your institute. And as advertised, I'm going to be giving a talk. So it's going to be probably a different kind of a talk that you guys have been probably used to thus far, because I'm a theorist and essentially a mathematical physicist, and I don't do pictures. So my talk has no pictures. The best it's going to be having are some sketches, some figures, hand drawn. So it'll be like a school or a classroom lecture. I guess I'm a teacher, and that is something which stays with me whenever I get a chance to speak. Except of course at conferences, because there the time is relatively shorter. Okay, so here we go. So so what I have in mind is to actually maybe with a modicum of levity could be probably just thought of as this, that I draw a cone, and it's going to be QCD served on the cone. Okay, so that's essentially what I'm going to be talking about. But to be more specific, let me try to think of um, a guideline or an outline for the talk. And I think I already have a file for that. So let me just share that with you. I'm not sure I'll be able to cover the entirety of this outline. It's probably too ambitious for 1 hour, but I'll give it a shot. Let's see. So we are familiar with basically the interactions, the four interactions of the universe, and we are, I believe, to some extent familiar with the so-called standard model of particle physics. And it is one of those interactions of the four that I'm going to be, to begin with, looking at. But the idea is going to be to actually look at a unified way of understanding all four, and therefore also QCD. So QCD, as I'm sure we all know, is short for quantum chromodynamics. And so that's going to be the strong interaction analog of quantum electrodynamics, which is something probably we are more used to, which is essentially a quantum theory of photon-electron interaction. So I'm going to be obviously not. I shouldn't say obviously. I'm going to be essentially working in the framework of what is called as string theory or superstring theory. And I'm going to be talking briefly about the notion of the different kinds of perturbative string theories, a so-called embarrassment of riches. And I'm going to be talking about its non-perturbative completion. I'm in that context going to be talking about point number 7, the so-called M and F theory. M theory is going to be in a restricted sense, and the more conventional sense. And we're going to be talking about how to incorporate the non-abelian gauge groups that we are used to or expect from a standard model, starting from string theory. Just give a brief introduction of, in this context, I'm going to be talking about essentially two kinds of approaches. One is the so-called large volume scenarios LVS D-brain model approach to realizing the standard model, which is partially or partly inspired by the so-called intersecting brain model. And the other is going to be the F-theory gut program. Okay. Now, the F-theory gut program is something, gut is, of course, short for grand unified theories. So this approach is essentially pure geometry. So in fact, it fits more with the theme of the talk, which has to do with understanding the math behind quantum chromodynamics, and more precisely, understanding the geometry or understanding QCD from just geometry. Of course, that's not really strictly correct, but I mean, geometry is going to play a very important part. Then we're going to be coming to essentially a very specific kind of six-dimensional manifolds called conifolds, and alluding to the so-called the famous conjecture of the so-called ADA-CFT correspondence, a la Maldacena, Juan Maldacena, which goes by his name, the Maldacena's conjecture. I'm going to be making inroads into generalization of this duality to what is referred to as, broadly speaking, gauge gravity duality. And in this context, I have a few things in mind to talk about. So the KW is short for Klebner-Witten. KS is short for Klebner-Strassler. Well, Huang is the name of a string theorist. And then McGill is the McGill model is again a model given by, I would call it now, the McGill diaspora. And we'll try to summarize our learnings at the end. Okay, so let's start. So I think just for completeness, I'm just mentioning the 4 interactions that we are familiar with. So to varied degrees, perhaps. So of course, we have electromagnetic, we have the weak, we have the strong. I'll put a little line below number 3, and then the 4th, the most commonly experienced, is gravitational. Okay. So the reason there is a dashed line beneath the 3rd interaction, which basically is a partition. Coincidentally, the partition is 1, 3, which is a signature of the Minkowskian spacetime that we love and use ubiquitously in physics, at least relativistic physics. So the reason for this 3-1 partition here is very different, and that is simply to do with the following fact, that the toolkit which works for understanding the first 3, in other words, quantum field theory, does not when studying gravity. Okay, so the best that you can do is maybe work with this approach only as an effective theory, as an effective field theory. That is the best that you can do. But otherwise, you fail miserably. Now, so one of the things which is therefore a consequence of this is that if you would like to quantize all 4 interactions, so since the 70s, nobody talks about the electromagnetic and weak separately. So this is referred to as the electroweak theory. So I guess elementary particle physics, there are two sets of GSWs. So this is one of them. So G is Glashow, S is Salam, W is Weinberg. Okay, Salam is of course unfortunately not with us, but Sheldon Glashow and Stephen Weinberg are still there, and Glashow, if I remember, is at Boston. Stephen Weinberg is at UT Austin. I think probably still is a director of the Institute of Gravity over there. And then we have strong interactions, of course, and that's where QCD comes into play. So that's the acronym for quantum chromodynamics. Okay, as far as gravity is concerned, so it turns out that in addition to actually quantizing gravity, one is also able to unify gravity with the remaining three interactions. And the two approaches out there, which people usually refer to, so maybe I make it a little colorful. One is string theory. The other is loop quantum gravity. I'm given to understand that there has been already a talk, at least a talk on both topics. So that, and loop quantum gravity is not my area, and therefore I'll have nothing to say about it. I will have a few things to say about string theory, which is what I work in. So as I said, there are going to be no pictures. I apologize again. So it's going to be just the whiteboard and various shades of various colors. Okay, so I'm not very sure about the composition of the audience, or probably the would-be audience. So I'm assuming a mixed bunch. So I think let's start with the very basic, which is essentially, let me just compare QED with QCD. And this is obviously not a comprehensive list. There are only a couple of things that I'd like to point out. And the first, and probably the only thing that I'm going to be referring to, is that this theory, okay, one of the things, this is an abelian, the gauge content of this theory is, it's an abelian theory, abelian gauge theory, excuse me. On the other hand, QCD is a non-abelian theory. So abelian usually, so the abelian group is just the phase is a collection of local phase transformations denoted symbolically by U1, and the non-abelian gauge symmetry in QCD is, sorry, SU3 color. The second is that this theory exhibits confinement. This does not. Okay. So to make it slightly more quantitative, so that it doesn't appear that it's all words, so we probably are familiar with the fact that when we study renormalization in quantum field theory, we talk about the flow or the variation with energy of the coupling constant. So we talk about a bare coupling constant which doesn't run with energy. Then we talk about renormalized coupling constant which does run with the energy. And typically, what one considers is a logarithmic derivative, the derivative of the coupling with respect to the log of the energy scale. So if I define the beta function for QED as beta sub QED, okay, so this is the scale mu delta E over delta mu. So this is the variation of the renormalized E with respect to the log of the energy. And so it turns out that if you're working in the perturbative regime, so if you actually do this by some calculation, you would have the need to actually invoke some regularization. So typically, the one that is used is a dimensional regularization. So essentially, there we talk about looking at the deviation from 4 of the space-time dimensionalities. So we typically that is denoted by epsilon. And the gauge coupling, of course, so what we are assuming is that the E squared, so we know that E squared over 4 pi h bar c. So I'm going to be working always with h bar and c equal to 1. Yeah, so that's the usual story in particle physics. So essentially, E squared is the fine structure constant of QED. And so we realize that this guy turns out to be a positive number. It is E cubed over, I guess, 12 pi squared. And the bottom line is it is positive. On the other hand, if you look at the QCD beta function, so let's call that beta QCD. So we know from, I mean, again, there's a standard calculation. If you've taken a first course on, or maybe a second, I don't know, some course on QFT, especially its application to particle physics, chances are that you've already done this calculation. And you end up with minus g cubed over 16 pi squared into an expression which is essentially group theoretic. I'll just write it down. It is 11 thirds C adjoint minus 2/3 times CF. So don't worry about these C's. I mean, they are basically group theoretic factors, as I said. So if you're working with the adjoint representation, you can look at essentially the trace of the trace of a product of the generators of the adjoint representation, and that turns out to be proportional to the to this constant which is appearing here. So for the adjoint representation, so C for the adjoint representation of SU3, this number is taken to be 3. And the idea is that this turns out to be negative. Okay, so this is going to be a very important feature, which essentially tells you that if one were to look at this theory from a so-called holographic point of view, in some sense, this is actually reverse holography. So holography typically says that you can encode information about the bulk on the so-called surface of the bulk. Here, you're going to be going from the surface into the bulk. Okay, but there's good reason for doing that. So the statement that I was making, but I did not quite complete, I apologize, which is that if you try to carry out a program of a holographic study of theories in the same equivalence class as that of QCD, let's call them cousins of QCD, then it should have this feature that it is infrared confining. Okay, so the features required of a QCD-like theory is that there should be infrared confinement, there should be UV conformality. If you solve this equation, you can see immediately the following, that if you are in the UV at very large energies, then the fine structure constant vanishes. It becomes very small. However, if you are in the infrared, then you end up with what I've already said, infrared confinement. In other words, the gauge coupling decreases with the increase in energy and vice versa. And additionally, you would want your quarks to transform in the fundamental representation of the group, the symmetry group. Okay, so any theory which, so this is required of a holographic theory. Okay, and so maybe I'm going to be calling this as cousins of QCD. Okay, so I probably should have said this earlier. The main idea behind this talk is actually to give just a little flavor of the following fact, that holographic studies in particular that is, in fact, slightly unobvious, which is the reason I would like to talk about what I'm going to be talking about. But in general, theories like string theory, superstring theory, and their non-perturbative completions, referred to as M and F theory, exhaust almost everything that pure mathematics has thus far offered. In other words, in this talk, hopefully, we'll get some flavor of topology, algebraic, differential, algebraic geometry, I should probably just include differential geometry here as well. Group theory. This is an O, not a 6. And what I would not be covering is number theory, partly because this doesn't figure in my research interests thus far. Okay, so let us begin. So till 1995, there was, as I verbally stated, an embarrassment of riches. The reason being that there were 5 consistent super, okay, maybe I don't need the double quotes, string theories which quantize gravity, and in principle possibly could have, is a big possibly, could have unified all 4 interactions. But irrespective of that expectation, there were 4 consistent so-called superstring theories. The title super, as probably we are familiar with, if not, it is not an adjective to indicate that it was, well, incredible. Well, maybe it is or was, I don't know. But the reason for the use of super here is because of an isomorphism between the 2 statistically different particles, bosons and fermions, implying that for every boson there is a fermion and vice versa, and that is in short referred to as SUSY, or supersymmetry. Clearly, there is no such symmetry, at least up to about 13 TeV, as verified by CERN at the Large Hadron Collider, in our nature. I mean, in nature. That means up to energy scales that we have thus far been able to explore, there is no, let's call it, low energy supersymmetry. Okay, so that is in itself a challenge, that if one wishes to connect a theory possessing supersymmetry, and by the way, this also happens, as we might be familiar with from probably some Discovery Channel lectures or what have you, is that these guys are actually defined in not 1 plus 3, but 1 plus 9 dimensions. So, so we've got 2 issues at least to address. One is, how does one go down the dimensional ladder from 10 to 4? And as we will quickly see, in fact, maybe even 11 to 4 or 12 to 4. But on top of that, we need to figure out the way, or the correct set of ways, if it's a non-unique set of ways, of coming down the dimensional ladder in such a way that you break supersymmetry, at least up to the energies that have been explored in nature. So if you want to make contact with real physics, you should come down to 4 dimensions and break supersymmetry. That's a very tall order. Okay, so and these have names. These 5 superstring theories have names. I'll just rattle them. I'll just write them down. They're so-called type 1, type 2, and heterotic. Okay, so type 1, type 2 heterotic. So the 1 and 2 roughly refer to the amount of space-time supersymmetry. Type 1 has to do with open superstrings. And if you, of course, join the endpoints of the open superstring, you end up with a closed superstring. And type 2 has to do with only closed superstrings. And it was a very non-trivial concept of actually introducing open strings in an otherwise closed string theory via so-called D-branes or Dirichlet branes, thanks to Joseph Polchinski. Heterotic is basically a marriage or a heterosis of a non-supersymmetric bosonic string theory in 26 critical dimensions with a superstring theory in 10 critical dimensions. So, in fact, this goes by the name of, there is a so-called a string quartet of Princeton, which is involved. That is not a musical composition or musicians. It's a set of 4 physicists, string theorists. And in fact, one of them went on to win a Nobel Prize, David Gross, not for his work in string theory, but for his work in QCD. But he certainly is a string theorist. Okay, so I still haven't mentioned, so I think this I've mentioned that it is an embarrassment of riches for the clear reason, the evident reason that there is no unique, at least till the mid-90s, there was no unique superstring theory. There were 5 of them. So then came the so-called string revolution, the second string revolution. Of course, the first being when one of the co-founders of string theory, John Schwartz, and the other, Michael Green, published a paper which actually put string theory on a very firm footing. So this is the second string revolution, and somebody by the name of Edward Witten at IAS Princeton, that's Institute of Advanced Study Princeton. He's the only physicist to have received the equivalent of a Nobel Prize in math called the Fields Medal for his work on so-called Chern-Simons theory and knot theory. So he actually showed that the various corners of perturbative string theory, which are these 5 consistent string theories, perturbative is important. For God's sake, that's a U, not an O. Actually have a one-dimensional higher common origin. And that is essentially called as M theory. Amusingly, nobody knows what the M stands for, but it was a term coined by Witten, and it has been used ever since. People like to amusingly call it mother of all theories and so forth. Maybe it is. I don't know. Maybe even Witten doesn't. But the idea was that using a beautiful feature of string theories, which is referred to as dualities. So there are in particular 2 kinds of dualities, broadly speaking, a so-called T duality and an S duality. This guy is going to be pretty useful, especially from an algebraic geometric point of view, that will be alluded to about half hour from now. Oh, I only have probably half hour. Let's see. Some minutes from now, let's put it this way. So the T duality is target space duality. So in short, it basically says that in words, there is no distinction between the small and the large. No distinction between the small and large. And S duality says that there is no distinction between the strong and the weak. If only our society could conform to these dualities, it will be so nice. Okay, that's the short, real short version of these two dualities, but it is essentially what I've written. So what it basically says is that if I were to look at the non-compact directions, and let's look at any one of them and compactify them to a circle. So, for example, if I consider my 10-dimensional space-time, which maybe is written something like as R1 comma 9 times S1, sorry. Okay, so it was, to begin with, it was R1 comma 9, and now it's one of the non-compact spatial directions has been compactified into a circle. This is a circle. That's how mathematicians denote a circle. And then we do the following. We say that if I look at the so-called type 2A closed superstring theory, and I compactify this theory on a circle. That's my symbol for compactification. Without getting into the detail, it just simply means that if you were to look at the real line, imagine identifying the endpoints of that real line. Okay, so you'll get a big circle. So that is the circle that I'm talking about. And let's say that this circle has a radius r. And then, so that's one. And the second is, I look at, by the way, what characterizes the so-called type 2A string theory. So this is a theory which, because it is closed, just like from wave propagation, we can think of this as consisting of left movers and right movers, the left moving modes and the right moving modes. So we have essentially associated spinners, let's call them the left spinner and the right spinner. And type 2A basically says that the left and the right spinners have opposite 10-dimensional chirality. You're probably familiar with the notion of chirality from 4D physics. You probably are familiar with the fact that, for example, if you look at the Dirac-Lagrangian, then the massless Dirac-Lagrangian possesses a chiral symmetry. The mass term is what breaks that symmetry. So this is a 10-dimensional generalization of that. So remember that the chirality operator is going to be involving a product of the generators, all the generators of the underlying Clifford algebra. So you just you consider the product of the Clifford algebra in 1, 9. So these have opposite chiralities, and the overall the theory is left-right symmetric and non-chiral. On the other hand, let's look at type 2b. I'm not going to write to save time. Still, it is a closed superstring theory. This time, it is compactified on a circle of radius 1 over r. Strictly speaking, what I've written as 1 should be written as alpha prime over r. So alpha prime is essentially the string length squared. Okay, so length squared over length is length, so you're replacing length with length. But if alpha prime is set equal to 1, in those units, you're looking at inverting the radius. So now this guy, on the other hand, has the left and right spinners having the same 10-dimensional chirality. So it's a chiral theory. The claim is that these theories, which looked very different in 10 dimensions, are actually the same in 1 dimension lower. So that's your T-duality. All right. Now, another example, let's continue with type 2b. So it turns out that the massless sector of type 2b has a bunch of scalars. In fact, it has 2 scalars. They are called the dilaton and the axion. We all know that there are a bunch of axioms. This is a kind of an axiom. Okay, so the dilaton is usually represented by phi. The axion is usually denoted by an A. And for later use, we're going to define a complexified axion dilaton modulus as A plus I. The triple line means I'm defining. So tau is defined as A plus I e to the minus phi. Okay, remember these are actually fields, and in some eventually field operators when you promote them after when you want to quantize the theory. And one can actually argue that the exponential of the vev of the dilaton is what gets identified with the string coupling constant. Okay, so we have the axion dilaton modulus. In addition to this, there are actually a pair of two-form gauge potentials, which are part of the massless spectrum of type 2b, the so-called NSNS two form, which I'll just write as BMN, and the so-called Ramond two form, which I'm going to write as, let's say, maybe CMN. So M and N are 10-dimensional indices, therefore they're taking values 0, 1 through 9. Okay, and these guys are actually antisymmetric. If I think I was given to understand by Dr. Das that tensor calculus is part of the curriculum of physics courses, so I think we can understand that we've got antisymmetric tensors. Then they are very nice when you want to take their derivatives to produce other tensors. So it turns out that there exists an SL2Z symmetry. The SL2Z, as we probably are familiar with, is one of the classical Lie groups. So it's basically all M's, which are written as A, B, C, and D, where, of course, A, B, C, and D are valued in the set of integers, such that determinant of M is 1. Okay, in case this is not very clear, this is an S, special linear group. Yeah, under this SL2Z symmetry, two things happen. The axion dilaton modulus undergoes a fractional bilinear transformation that we're familiar with from conformal transformations. We have A tau plus B over C tau plus D. Okay, with this constraint. And the second is that the axion, sorry, the pair of two forms, the BMN and CMN, they undergo a transformation in which they're actually multiplied by an SL2Z matrix. Okay, so in other words, the SL2Z transformation mixes the so-called NSNS Ramond sector. So the NSNS Ramond are just names for respectively antiperiodic and periodic boundary conditions. So the claim is, by the way, if I look at this particular transformation, I think that should suffice. What we notice from here is that if I switch off set axion to 0 for simplicity, then for appropriate values of A, B, C, and D, one can see that the dilaton under an SL2Z gets mapped to negative of itself, which means the exponential of the dilaton is going to be mapped to exponential of minus of the dilaton. When promoted to field operators, and when you take a vev and exponentiate the same, that is the same thing as saying that the string coupling would be mapped to the reciprocal of itself. That's the punch here. The punchline for this part of the example is, it says that if you are working with in a sector of the theory where the coupling is very large, so therefore you are not able to do perturbative calculations. With the application of a strong big duality symmetry, in other words, SL2Z symmetry, you can actually map the theory to another corner of the same theory where the coupling constant is small, and therefore the theory becomes amenable to perturbative calculations. So that's an incredible statement. Usual non-supersymmetric theories do not possess such incredible symmetries. So these are two examples that I wanted to give to actually state the claim of Edward Witten, which is that all perturbative string theories arise from a single 11-dimensional theory. Okay, so there is a whole network of dualities which is actually used to arrive at that statement. And another cool thing is that the 11th dimension actually arises if you hike up the coupling constant. In other words, there's a direct connection between geometry, the size of the 11th dimension, which is a circle, if you wish. So the size of that 11th M theory circle with the coupling constant of your theory. Higher the coupling constant, or stronger the strongly coupled the theory becomes, that is equivalent to actually opening up an extra dimension. Okay. Now, so probably one of the most famous students of Edward Witten is Kumram Waffer. He is at Harvard. And interestingly, he gave what is referred to as F theory, which is in fact 12-dimensional. Again, some people joke, M is the mother of all theories. It should have a father. That's the F theory. But that's not really something I would like to advocate. Just a little levity once again. That was about it. So here, I'm going to basically make a small detour and talk about a series of nested blobs. So imagine that I have a big blob over here, and I'm going to call this as M sub r. Then I'm going to have another blob, and I'm going to call that as Mj, a smaller blob that I'm going to call as Mc, yet a smaller blob, I'm going to call that as Mk, and in the interior, what I'm going to be calling as Mcy. So Mr is going to be, it's supposed to represent real manifolds. Mj are going to be real manifolds of even dimensionality with an almost complex structure. Mc are going to be complex manifolds with an integrable complex structure. Mk is going to denote Kähler manifolds. The double dot is German, is called Umlaut. It's supposed to combine the sound of the given letter with E. It's not Kähler, it's Kähler. Kähler manifolds. And finally, Mcy are Calabio manifolds. So Calabi and Yao are the names of two mathematicians, one alive and one not so much. Yao, Xingtung Yao is probably one of the most famous practicing mathematicians, heavily involved in string theory as well. Again, a Fields medalist, but a mathematician Fields medalist. So there was a conjecture given by Calabi, which was proven by Yao, and he got the Fields medal for that. Well, I'm not sure if he got the Fields medal for that, but well, the manifolds satisfying that conjecture are called as Calabio manifolds. They're ubiquitous in so-called string compactifications. Now, amongst these Calabio manifolds, so there is another notion in uh, in math, which is the notion of fiber bundles, that you can sort of think of as a cartoon. That imagine you have a collection of bristles and you have a handle. So this, as is evident, has to be the base. These bristles are the fibers, and the collection of these fibers over the base is a fiber bundle. Okay, so that's a cartoon. What it actually implies is it's actually a collection of some topological spaces. And if it turns out that you have the fiber, which is an elliptic curve. So let's say there's a fiber which is something like a 2 torus. Yeah, so that's like roughly, yeah, it's like S1 product of circles, jalebi or donut, tire tube, or what have you. So, so in other words, we have the following picture in mind. So imagine that I have a complex threefold B3. So the 3 is the complex dimensionality of B. And at every point of this B3, I erect a torus. Okay. The cavity inside there is the hole that you have in a donut, yeah, or a tire tube or jalebi or imarti. So and it is not necessary that these tori have the same sizes. In fact, at some point, so if I draw again a torus like this, I can imagine drawing a loop like this, and I can imagine drawing a loop like this. Okay, so these are, if you wish, the 2 circles that I was talking about here, or so-called 1 cycles. And it may happen that maybe at some point, one of these cycles it actually degenerates. So maybe you have something like this, like a croissant. Okay, so people talk about pinching of a cycle, and if somehow you can surgically excise this, then you would actually be having topologically an S2 or 2 sphere. So the definition of F theory is as follows, that F theory compactified on an elliptically fibered Calabio fourfold, which mathematically is written in the following way, that I have a T2 fibration over base B3. The B3 typically is not a Calabio itself. I haven't defined what a Calabio manifold is. I haven't defined what a Kähler manifold is. So that's because of the time constraint. I'm just saying that please refer to the blobs, the series of nested blobs that I had mentioned. Yeah. So it's a very, very special kind of a complex manifold. So if I have this 12-dimensional F theory, which is compactified on elliptically fibered Calabio fourfold, the claim is that this is the same as type 2b, compactified on the base of that elliptic fibration, such that the complex structure of the T2 gets identified with the axion dilaton modulus of type 2b. So the complex structure of the T2, so the T2 can be thought of as essentially the so-called fundamental domain of the torus can be thought of as a parallelogram. So what you can do, imagine in your minds, is that you have a parallelogram with this complex number 1, there's a complex number tau, there's a complex number tau plus 1. So if you wish, this is the tau that I'm talking about. This is what is being repeated throughout. Okay, so you've identified this with this and this with this. That's what gives you that tubular structure, if you wish, the toroidal structure. So so it basically connects geometry with field theory directly. with string theory directly. Okay. Now, so now that is as far as mentioning M theory and F theory is concerned. Now, to make contact actually with QCD, it seems I don't have the time for. Obviously, I'm not surprised. I mean, I'm not surprised because I've already mentioned that I had an ambitious outline. I don't think I'll be able to complete it, but okay. So I just mentioned the following, that I had mentioned two approaches of trying to realize standard model from string theory. And the one of the approaches that I mentioned, which is the following, is that that goes by the name of F theory gut. Okay, so that is short for grand unified theories. Oops. Is the following. So so I mentioned that Joseph Polchinski was a guy. He unfortunately is no more. So he was at UC Santa Barbara, University of California, Santa Barbara. So he's a guy who basically introduced the notion of introducing open strings as a closed string theory via the introduction of topological defects. So imagine that I have a hypersurface, and I have an open string which is quote unquote pinned to the hypersurface, so that this guy can actually go like this, go like this, go like this, go like this, etc., but cannot come out. Therefore, it is pinned. Okay, so if the spatial dimensionality of this is P, this is what is referred to as a DP brane. Oops. Okay, so these DP branes are what get basically, as I said, they tell you a way of actually introducing open strings, this is the open string that you have, into an otherwise closed string theory. Now, it turns out that type 2A supports even dimensional branes, DP branes, the dimensionality being given by P, the spatial dimensionality. The spatial is never really explicitly stated. And type 2B has odd dimensional DP branes. So remember, I also mentioned in F theory that when you talk about this elliptic fibration, there are places where actually the fibration can actually degenerate. So it turns out that you can actually associate the places of degeneracy of the fiber. So degeneracy of fiber can be associated with locations of D7 branes. So the basic idea of Waffa and his student Jonathan Heckman. So this is given by Waffa and his student Heckman. Heckman, I think, right now is at UPenn. Is that the first is that matter fields such as quarks and leptons arise at the intersection of four-dimensional subspaces. I'll call them four cycles, sigma fours. I is indexing these four cycles. So these D7 branes are actually wrapping four cycles. So they are space-time filling. In other words, you have the Minkowskian R1, 3 as part of the so-called wall volume of these D7 branes. But then in addition to that, you also have 4 directions, which are compact and are wrapped around an object. A 4-cycle means a manifold that doesn't, roughly a manifold that doesn't have a boundary. So if you look at an intersection of multiple such 4 cycles, if you're looking at a collection of multiple D7 branes, so maybe there's a D7 brane wrapping a 4-cycle sigma 4-1. There's another D7 brane wrapping another 4-cycle sigma 4-2. And you look at the intersection of sigma 4-1 with sigma 4-2 for appropriate choices of non-abelian gauge symmetries associated with these D branes. Now, a point that I apologize I forgot to mention when I was talking about D branes. So I'll just make an arrow like so. So one can actually show that a stack of n coincident DP branes supports a UN gauge theory. Okay, you can sort of factor out the center of mass, and then you just have an SUN. So what you now have is actually a stack of D7 branes wrapping a 4-cycle sigma 4-1. You have another stack of D7 branes wrapping another 4-cycle sigma 4-2. And the intersection of this is maybe a 2-cycle. So at the intersection of these 4 cycles, so you'll have an open string, which would be starting from maybe one of the 4 cycles and ending on the other 4 cycle. So at the intersection, you have a so-called enhanced gauge symmetry. So there exists enhancement of symmetry. There is a beautiful theory in mathematics which goes by the Kodaira classification of singularities of elliptic fibrations, which actually associates gauge groups with the kinds of singularities and elliptic fibrations in algebraic geometry. Okay, so there is an enhancement of symmetry, and so the phenomenologists amongst us would be also worrying about Yukaba couplings. So the Yukaba couplings arise from a triple intersection of 4 cycles. You'll have sigma 4 intersection sigma 4, call it 1, 2, and 3. So these are the points of triple intersection. Okay. So the other way of trying to realize standard model was large volume scenarios, is something which I have worked with a couple of my students, but since I don't have time, I will not be talking about it. I haven't worked in F-theory guts, but because of this geometric nature, it's really a very interesting setup for me to at least mention. And in fact, the authors also essentially tried to argue why there are only 3 generations of quarks and leptons. And that essentially has to do with invoking, making a comparison with what is called as the Frogat-Nielsen mechanism of generating a hierarchy in, just in particle physics, in BSM physics, so-called beyond standard model physics. I'll just not say anything more about that. Finally, so Dr. Das, can you please tell me how much time am I left with?
About another 10 minutes, 10 to 15 minutes.
Okay, great, excellent. Thank you so much. Okay, so now I would be talking specifically about QCD, and now actually addressing the notion of a cone. So there is a famous picture which is actually drawn when you talk about the cones that I'm talking about are, strictly speaking, what are referred to as conifers. Okay, so the picture that I'm talking about is the following. So imagine that I draw a cone in the following sense. This segment is supposed to denote a 3-sphere. This segment is supposed to denote an S2. So roughly, what I have is a 5-dimensional manifold, which is a product of a 3-dimensional sphere and a 2-dimensional sphere. And these guys are these slanting sides are actually, if you wish, supposed to denote a radiant direction. And this is the apex of the cone, where obviously you have a curvature singularity. Now, this is what is called as a singular conifold. And this was actually extensively studied, especially in the context of trying to make contact with string theory. It was initiated by the husband-wife duo of Phil Candelas and Zena Delosa at Oxford. It's a nice 1990, if I'm not mistaken, nuclear physics B paper in which they talk about conifolds. Now, there are two ways of actually desingularizing the conifold, and those are the other two pictures. So maybe I think what I do is, oh God, what did I do? Seem to have lost what I was writing on. Okay, I think instead of wasting time trying to find where I was, let me draw that picture again. So there's a conifold here, a singular conifold. This is S3, this is S2. I'm going to desingularize it in two ways. The first is I'm going to draw a picture like this. Sorry. So what I've done is what was initially an apex has been quote unquote blown up into a 3-sphere. This is your S3, this is still your S2. The other way to desingularize is therefore clear. Well, this is topologically a line segment. This is now an S2 blow up. This is S3. This is S2. So this is called an S3 blow up and has a name. It is called a deformed conifold. And this is what is called as an S2 blow up. And this is what is called as a resolved conifold. Okay. Now the question is, how does this have anything to do with QCD? And that's where the story begins. So I should mention, of course, the Maldasena's conjecture. And that essentially says that I would state it very, very loosely and imprecisely, but intentionally. So it basically says that a supersymmetric gauge theory in the very large Truft coupling limit so the Truft coupling, so let's say if I have an SUN gauge theory, so with the gauge coupling G Yang-Mills, I mean non-abelian gauge theories are synonymous with Yang-Mills theories, right? So G Yang-Mills squared times n is the Truft coupling lambda. So we're going to be looking at the limit where the G Yang-Mills is going to 0, n is going to infinity in such a way that lambda is very much larger than 1. It turns out that you can argue that the natural perturbation parameter in these gauge theories is actually lambda itself. So clearly, if lambda is very large, you can obviously not resort to perturbative calculations. So therefore, not therefore. So that's where the power of the conjecture lies, because what Maldacena said was that you can actually do the computation in a classical theory of string theory called supergravity. This is actually supergravity, field theory limit of string theory, and the classical limit thereof, supergravity, and that's it. So this is a 4-dimensional theory. This is a 10-dimensional theory. Okay, it turns out that in the original form of this conjecture, the 10-dimensional manifold that was used was a 5-dimensional anti-de Sitter space times a 5-dimensional sphere. And this guy was actually, if you wish, the boundary of a Euclideanized ADS space. Okay, so this S5 was just going for the right, if you wish. It's basically the boundary of ADS5 is where the gauge theory lives, and you capture the information, the strong coupling limit, by going into the bulk. Okay, now, as I mentioned in the so-called outline, the broader area since the conjecture goes by the name of gauge gravity duality. Okay, so there are 4 parts of the story. I obviously do not have the time to go into any of them in detail. I just mentioned them. So the first was the story started by Klebanov and Witten. Klebanov is at Princeton, Witten is at IAS Princeton, and they talked about actually realizing a supersymmetric gauge theory on a conifold. So in other words, in the so-called near horizon limit, the near horizon limit essentially says that the radial coordinates value never exceeds, or is always much lesser than, a certain length scale that you associate on the supergravity side. So that's the so-called near horizon limit. So this actually becomes an ADS5 cross so-called T1, 1. This is a so-called Sasaki-Einstein 5-fold, which in this context is essentially S3 times S2, which is the so-called base of the conifold. So the conifold is actually an example of a non-compact 6-dimensional Calabio manifold, 6 being the real dimensionality, where you have a non-compact radial direction fibered over a Sasaki-Einstein base, which itself is an S2 fibered over S3, is essentially S2 times S3. Okay, so what this had was essentially a collection of so-called D3 branes at the tip of a singular conifold. Okay, so the singularity of the conifold was actually utilized. So I remember I mentioned that there is a connection between singularities and gauge theories. Singularities, let's say in the earlier context of elliptic fibrations, where there is a degeneracy of the fibration, and a corresponding gauge theory. So here, similarly, you have a singularity associated with the conifold at the tip, and there is a connection of that with actually a supersymmetric theory, which is living on the D3 branes placed at the tip of that conifold. So this theory had the feature that it was a conformal theory and supersymmetric. Then came Klebanov cyclone. I don't recall the years, it's early 2000s. Okay, and they actually, so the Klebanov-Witten basically had just D3 branes at the tip of a conifold. These guys had actually D3 branes and D5 branes wrapping the vanishing S2. There is actually a vanishing 2 cycle or vanishing 2 sphere in a singular conifold geometry, which is part of the reason why you have a curvature singularity. But this theory actually ran into problems in the infrared. Those were actually rectified by Klebner-Strassler. So there's a similar setup as here, but using so-called strong dynamics in the infrared. They actually showed that this model had infrared confinement. But was supersymmetric. And there were no quarks. Then came Peter Wang. He talked about introduction of D7s in the conifold geometry. And essentially realizing the quarks as D3, D7 strings. Supersymmetric. Then there were a collection of attempts, which I frankly don't recall in terms of the chronology, but I would say that there were attempts by, again, Klebanov, by oh, this is embarrassing, I'm forgetting the name. Others, okay, for finite temperature version thereof. And you can naturally break supersymmetry with the introduction of a temperature, but there were various kinds of problems. And then we end up with the McGill construct, McGill model, that actually combined everything before them and was UV complete. And non-supersymmetric. And had quarks. Oops. The fundamental representation. So maybe in the last, I don't know, -2 minutes, so I hopefully 1 minute, I've just briefly mentioned the following. Dr. Das, can I just take 2 more minutes?
Yes, yes, you can.
Okay. So I just want to squeeze in just a tiny bit of our effort in this direction. So starting from essentially 2013, what we actually tried to address was holographic QCD. This is a so-called top-down approach. The top-down means that you start from a higher dimensional theory and systematically come down to 4 dimensions instead of cooking up a model, which is a bottom-up approach. I'm not belittling either one of them, it's just that's what they are. So holographic QCD at intermediate gauge or Truft coupling. So clearly, if your coupling constant is no longer very small, you can no longer stay within the perturbative description of string theory, which is what actually led us to what we dubbed, frankly, as Mqgp, the so-called Mqgp limit. I'm by no means a practitioner of QGP, quark gluon plasma, but the only reason why we basically dubbed this limit as the Mqgp limit is because the string coupling was no longer small, I should say very small. And practitioners of QGP tell us that holographic models should actually incorporate that. And because the string coupling is no longer small, it necessitates addressing this limit from M theory. So strongly coupled gauge theories, when studied from a top-down holographic approach, necessarily requires one to actually start from M theory, which is supposed to be the non-perturbative completion of perturbative string theory or string theories. So in that process, what we were required to do was to actually utilize what is referred to as the Strominger-Yau-Zaslow, or SYZ, mirror symmetry. I wish I had the time to explain, to motivate this, and then maybe say a few words, but since I don't, I would not even try. But this is something that would be required to actually go from type 2b, which is the kind of closed superstring theory in which the Miguel construct was originally defined, to type 2a. And using a prescription due to Witten, quote unquote, uplift the type 2a SYZ mirror to M theory. Okay, then with my students, I learn a lot of things from my students. I'm very proud of that. So in fact, they teach me a lot of physics, a lot of contact with physics, and we successfully have tried to actually match data numbers from data, including particle data group, PDG, data values, lattice calculations, with a whole bunch of things, and on the phenomenology side, and also in terms of temperature dependencies of various transport coefficients on the kinematic physics side. I am neither. I'm not a phenomenologist. I'm not a kinematic but a physicist. But it has been a good ride, a good fun, and I think that is where I'll pause. So thank you for your patience. Maybe we can have questions.
Thank you, sir, for your wonderful presentation, for your wonderful lecture, actually. So it's like a classroom for a student. So thanks for giving us time. So we have got few questions in comment and in inbox. So if we allow, we can start
Please,
our
please. Yep.
discussion session. So the first question: what is the holographic theory?
Okay. So should I close this whiteboard and just turn on my camera? I mean, and so that should I
Yeah. You
do
can.
that?
You can. You
Okay.
can.
All right.
Yeah.
Let me do that, please. Okay. So okay, holography. So what I had actually said earlier was that when you want to study features of a certain d-dimensional theory, it could be QC, it could be something else. And in this context, you try to do that from a higher dimensional theory. So in that sense, that is the reason why I use the term reverse holography. So you want to study four-dimensional QCD, and you realize that you would like to study it from a quote-unquote fundamental theory. And it turns out that the fundamental theory out there is a higher dimensional theory. So you therefore try to study a four-dimensional theory from maybe a 10-dimensional theory, such as superstring theory, or an 11-dimensional theory, such as M theory, or if the need so arises, maybe a 12-dimensional F theory. So that is, in this context, the meaning of holography.
Okay, sir. We have got another question. So what is the M theory?
Yeah. So as I mentioned during the lecture, M is supposed to, I don't know, nobody knows what M stands for. But in this context, it is supposed to be, so maybe, so there is a very famous picture which is made. There's like a star where the five cusps, you have like five cusps. So you have these five cusps which actually denote the five perturbative descriptions of string theory. And in the middle, you have M theory. That is a picture that was advertised. Maybe it was also on one of these strings conferences bags, which was organized roughly at the time when Witten gave his revolutionary idea. So that basically says that the 10-dimensional string theories, which look different as they look different, they look as five different 10-dimensional theories. If you go one-dimensional higher, then those five perturbative string theory descriptions can be shown to arise from an 11-dimensional common origin. That common origin is called M theory.
Sir, thank you. So we have another question. So is that coupling is related to nuclear force?
Okay, so if you want to actually calculate, if you want to actually calculate a so-called nuclear force and so forth, what you would like to do is resort to an effective field theory description. And whatever be your, so let's say that you actually, it is actually possible to make contact, for example, with what is known as chiral perturbation theory, which is an effective field theory routinely used in nuclear physics, starting from string theory. And so once you do that, then it is as good as working in a field theory and working out the force of attraction or repulsion, maybe, for example, or working out a potential, and including therefore getting the nuclear force, the nuclear potential. So the main issue is how does one make contact with a quote unquote fundamental theory with maybe a chiral perturbation theory or a baryon chiral perturbation theory, etc., and then you undo conventional nuclear physics. So the answer is yes.
Okay, sir, thank you. This may be the last question. So in condensed matter physics, one goes from bulk to surface, integrating those degrees of freedom, which are not good quantum numbers, followed by unitary transformation. But how do you go from surface to bulk, for example, reverse holography?
I'm not sure I follow or agree with what was said earlier in the earlier part of the question.
Okay, I can add the question.
Right. Yeah. So okay. So I'm not sure. Yeah, what is implied by what has been written here? As I said, I'm not sure I even agree with it. But in this context, what is when we say that you go from when you doing reverse holography, or nobody says the word reverse, they just use holography. All that is being said is that you're actually trying to construct a theory in the bulk, so that if you restrict that theory to some surfaces in the bulk, you'd actually automatically be addressing low dimensional physics confined to that surface. So that surface could be the so-called surface of a brane, a so-called D brane. So I had been talking about this, that if I have coincidence stack of D branes, it doesn't matter what the dimensionality is, you can actually argue that automatically would correspond to having a non-abelian gauge theory supported on the wall volume of this coincidence stack of D branes. Okay, so the idea is that how do we consistently embed those wall volumes corresponding to DP branes into a theory which is, let's say, 10-dimensional. So that is the so-called reverse holography.
Okay, sir. So as we don't have no questions, so we should conclude our discussion session. So thanks again for giving us this opportunity to arrange a webinar like a classroom. So thanks for accepting our invitation, sir. It's a great webinar with you. I think our students have learned a lot of things about this M theory and others, high energy physics theory and mathematical theory. So hopefully our students have learned in this mathematical part of this theory. So thanks again, and hopefully we will arrange another webinar with you in near future. And after the COVID, I would definitely invite you for a face-to-face session in our university.
So
bye for today.
Yeah. Bye. Thank you. Stay safe.
Yes.